Alright, so it's asking us to find the magnitude and direction of the field at a point P. Let's just start by writing Biot-Savart's law, which is equal to 4 pi times by the current, infinitesimal length over r squared. So the way I'm going to approach this is by separating each line into a separate segment, and then calculate the magnetic field of each segment and adding it all up. So let's start with A and C. Before I approach any of these, let's find out the direction. It's going to make things easier. dl times by r hat. R hat is a vector that points towards the point P, and dl is the infinitesimally small part of A or C. Because r hat is parallel to dl for d of A, it's just going to be 0, because when you cross two parallel vectors, it's going to be 0, because sine 0 is, of course, 0. 0, and the same thing goes for C. So we can just neglect these. Now, D and B. Let's start with the direction. R hat. So let's start with D. It's going to be Ri. I'm going to rewrite dl. dl obviously is the infinitesimally small part of small segment of the line D. So I'm rewriting cylindrical coordinates. So you have Ri, d theta. I'm going to introduce tangential vector theta hat, which goes in the anti-clockwise direction. But as the current is going clockwise, the tangential vector goes anti-clockwise, it's going to be minus. Recall that for very small angles, the radius times the angle gives you the small length here. Okay. And for Ri hat, we said that R hat is pointing towards P. We know that Ri is pointing away from P, so it's going to be minus R hat. Let's put these twos together. It's going to equal minus Ri d theta theta hat cross with minus R hat. Alright. So the minus signs cancel. So we're left with theta hat crossed by R hat. And for cylindrical coordinate systems, unlike Cartesian, it will give us negative z pointing into the page. So it's going to be Ri d theta z hat, but it's pointing into the page, so minus, because I've defined it as the negative. Okay, now solving for the magnetic field strength is going to be quite simple. It's going to equal I over Ri for r squared. Because it's a quarter of a circle, the bounds are going to be pi over 2, 0, d theta going into the page. This is quite simple. Without showing too much working, we can just calculate that. Ri 8. That's what we get for the magnitude of field strength at D. Let's try for B now. Alright, so let's do the same thing. We got dl times by r is r0, because that's the distance, r0. dl, this time the current is going with our tangential vector theta hat, so we can just do r theta d theta with no minus sign. But r0 is still going to equal minus r hat, because they're going opposite directions. Do the same thing as before, times these two. We're going to get r0 d theta theta hat cross with minus r hat. Again, Cartesian coordinates work differently to cylindrical coordinates when you cross product. Theta hat cross with minus r hat is going to give us positive z hat. So that's coming out of the page. So then we can work out, again without showing too much work in, the magnetic field strength at P from the line B, which is E equals R0 8. That's from B. Alright, now let's add the two up. We're gonna get, so B total, don't forget that, it's important. B total is going to just be over 8, 1 over R0 minus 1 over R I, Z direction. That's how you solve it.